We often mistake a state of control for stability. In reality, maintaining a specific alignment within a dynamic system requires continual adjustment. Natural systems tend toward homeostasis, a spontaneous balance where the system settles into its own trajectory without external intervention. Control, or allostasis, is an imposed regulation. It forces specific variables to remain within a preferred corridor, often working against the system's natural basin of attraction. This creates a persistent trade-off. While the controlled point may appear orderly, the effort of holding it there generates tension that must be absorbed or redirected elsewhere in the network. Within the brain kinematics model, we define this tension as strain, the measurable divergence between the system's natural trajectory and the imposed path. This begins with emergence. As the controller restricts movement, pressure builds where the system is most constrained. Then comes variation. Because no control signal is perfect, the system response fluctuates, creating a dynamic interaction between the applied force and the system's resistance. These fluctuations are compounded by feedback delays. By the time a controller senses a deviation and applies a correction, the system has already moved, ensuring adjustments are out of phase. Finally, the strain undergoes dispersion. It is not eliminated but redistributed into alternative pathways, often moving into zones where it is less visible or harder to measure. For any managed system, this cycle of emergence, variation, and dispersion represents a structural consequence of imposing order. Visible regularity is frequently maintained by storing unresolved tension in boundaries, delayed feedbacks, or downstream variables. If strain cannot be destroyed, the central challenge of any controlling force is determining where it chooses to hide that instability. The brain kinematics model lets us observe this mechanism at the biological level, human self-regulation. In this MRI series, we see the hardware of executive control. The prefrontal cortex manages behavior by interacting with deeper emotional systems. To deliver a speech, the prefrontal cortex suppresses fear to maintain a focused, fluent trajectory. Successful delivery is a form of momentary phase locking, a temporary alignment of cognition and emotion. But the underlying fear hasn't vanished. It reorganizes and disperses, often reappearing later as physical body tension, overthinking, dreams, or mental fatigue. At this scale, self-control redirects emotional load rather than removing it. We see the same pattern scale up to the social cortex of an economy, where control is distributed through monetary policy and regulation. When a central institution targets a single variable like inflation for rigid control, it fixes one node of a complex network. This regularity generates compensatory strain in connected nodes, as the market attempts to settle into its own balance. This creates dispersion pathways. As the primary target is stabilized, the pressure shifts into black markets, household debt, or social dissatisfaction. For instance, maintaining artificially cheap credit can force an appearance of balance today, while pushing the actual strain into future debt structures. Because market feedback is often delayed by months or years, these corrections are frequently out of phase, manifesting as cyclical boom and bust periods. Maintaining this surface-level stability requires the central institution to apply increasing effort against the system's pushback. Stabilizing one variable often necessitates destabilizing another, effectively moving the burden across the population rather than resolving the underlying pressure. At the macro scale, geopolitical empires attempt this same coercive control over vast populations and resources. Here, feedback delays are at their extreme. Information travels through massive layers of bureaucracy and distance, ensuring that central corrections are almost always lagging behind local realities. This control forces an artificial alignment onto distinct regional identities and autonomies that would otherwise follow their own trajectories. When this alignment is maintained through force, the strain disperses into corruption, migration, underground networks, or symbolic resistance. Historical longevity does not suggest an absence of strain. Systems like the Roman Empire managed to endure for centuries by successfully diffusing and postponing the release of compounding frontier and fiscal pressures. Rapid collapse occurs when the rate of strain generation finally exceeds the empire's adaptive capacity, leading to a sudden release of accumulated pressure. These patterns suggest that the same constraints of feedback and load found in human executive regulation also bound the largest geopolitical systems. Across all scales, from individual dreams to market debt to imperial rebellion, the structural response to rigid control is identical. Strain increases with distance from natural balance and control rigidity. As rigidity rises and adaptability falls, strain density increases. To manage the appearance of this strain, controllers often employ symbolic masking, the use of narratives, rituals, or statistics to preserve a facade of order. This masking can take the form of personal self-deception, optimistic economic forecasts, or elaborate imperial ceremonies. Masking delays the visible signs of instability, but it hides accumulating entropy within the system's foundation. Legitimacy is the only factor that actively lowers strain because it aligns the control with the system's own acceptance, reducing the need for rigid enforcement. A calm person, a stable market, or a peaceful empire may not be truly balanced. They are often simply well-controlled environments, holding a significant amount of internal pressure. Breakdown occurs when accumulated strain and feedback delays exceed the controller's ability to redistribute the load. This reveals the central paradox of management. You cannot fix a fracturing system by applying stiffer control. Increased rigidity only raises the strain density. Durable recovery requires restoring adaptive circulation, redistributing burdens, and reestablishing legitimacy to let the system breathe. Because perfect control is impossible, survival depends not on the elimination of fluctuation, but on guiding those fluctuations within sustainable, flexible bounds.